Hello, everyone, and welcome to this Telit Cinterion webinar, Harnessing Composite Variables for Real-Time Data Analysis. I'm Amanda Flink, the head of global events here at Telit Cinterion, and I will be moderating our event today. To explain this topic today, I am pleased to be joined by Gerhard Lapp, the Senior Solutions Architect for IoT Platforms at Telit Cinterion. Now, just before I hand it over to start our presentation, I do have just a few quick reminders for our audience. We will have time to answer a few questions at the end of the presentation. You can simply submit a question by posting in the questions box, which is located near the bottom of your screen. Also, please be sure to check out the resources section for some additional information. There you can find a few resources related to today's topic. And finally, we will send out this replay link to all attendees at the conclusion of the webinar. And with that, Gerhard, I will hand it over to you to start our presentation today.
Thank you very much, Amanda. I'm more than happy to provide this presentation, and thank you for the opportunity. Allow me to go over the numbers first to introduce a business perspective of this. So in today's market, we have 30 billion IoT devices, which will be online by 2025. And from a Telit perspective, we connect and manage approximately 1 million new IoT devices every week. Going beyond IoT devices, forecasts for the near future expect the market volume to reach 2.2 trillion by 2028. This is according to a source from Statistica, and we can certainly provide the link to that forecast. And it not only considers the IoT devices we are dealing with, but many industries are joining the technology and the solutions utilizing IoT technology, including industries like automotive, consumers, healthcare, industrial, and/or smart cities, as just a few examples. Versus the initial phase when companies discovered IoT and realized at the time the tremendous accumulative cost associated with onboarding single devices, we actually experience now a renaissance as cloud solutions provide the platforms to manage not only gigabytes, but petabytes of data cost effective and manageable. On-prem solutions are rapidly moving into the cloud, and many times corporate IT, if you may know, do not even provide our business units any options any longer. They simply force business units to move away from on-prem. This presentation, I'll demonstrate a solution which will enable you to not only collect your data in our current conventional way, but to transform the data in such a way allowing you to standardize your access to data sources, and by providing the connectivity to create a global distributed namespace representing individual and composite variables as well. A composite variable is a variable created by combining two or more individual variables called indicators into a single variable. Composite variables are used to measure multidimensional concepts that are not easily observed. In many cases, composite variables depend on local business processes. For example, if we consider OEE data, they provide information which is a combined set of data collected to calculate availability, performance, and quality. With this, please allow me to have a little discussion and view into the history of data collection and management. To understand this cartoon, the request from the executive management has always been, get me all the data I need. I think there was always this request from management that they need data sooner than later. In the early days, it took weeks sometimes when the reports were created on assembly lines, versus today they can actually literally watch in real time how the production performs. And this is part of the critical solution. We will discuss how to do this. And even though they request that get me all the data I need, there are still, even today, 3 problems which makes this request a challenge. In the early days, a communication standard did not exist among third-party systems. And this is still a challenge today, as we know. Process automation, even today, is very protective about accessing any data, potentially revealing the technology applied. Machine vendors who building machines are very hesitant and reluctant to introduce solutions directly onto their machine to allow easy connectivity, and they use all kind of layers, including OPC, to just interface with machines, but not to be part of the machine when collecting the information. And that's mainly the reason because they are protective. Um, Consequently, islands of automation were created as a result, and meaning that individual stations among individual assembly lines were unable to communicate with each other. So you kind of had to get the information available from the islands itself. And then last but not least, collect information about anything and everything, which Industry 4.0 is requiring today. The the challenge becomes, which data do I need to collect? I have tens and hundreds of thousands of data points in large process assembly lines. And then how do I choose the data I need and which makes sense to me in order for me to optimize my process? And of course, as a consequence, the goal is always to use a conclusive set of data, allowing me to optimize my process. When we look at the Industrial Evolution 3.0 and see the impact on manufacturing, the introduction of the Purdue model occurred about early 90s. And at that time, process automation actually experienced its first renaissance, which I call this. This pyramid and concept allowed all the hardware and software vendors on all levels, from the manufacturing process level all the way to the ERP level, to provide solutions focused on the task at hand based on the level they were designed for. And this created a very static model on all levels and actually very limited in what you can do because the application itself are focusing on the requirements for each level, whether it's PLC technology, automating the process or the manufacturing process, incorporating input and output signals for the field level and the process level, and then whether they were HMI and SCADA systems, MES systems, ERP systems, each with their own responsibility, and connectivity from one point to another or from one level to another was a challenge. That's where, at the time, at least for the lower levels, to connect HMI, SCADA, MES, and ERP to the process level, OPC was introduced to this concept. And then, of course, with the introduction of the PC at the same time, HMI and SCADA systems were introduced to interface MES, ERP, and PLC systems while providing user-friendly supervisory and production control functionality. For the first time, data from many islands of automation could now be collected to store them in relational databases for further analysis. Let's look at the reoccurring events, how we started from an industrial 3.0 evolution, the introduction of IoT, and the combination of these versions of connecting devices into IoT. The fourth industrial evolution was introduced in 2011, and with the arrival of I think, famous IoT solution, and you may remember this, in the same year called Ring Doorbell, it became obviously that combining both aspects of IoT and Purdue, industrial automation became now IIoT. So even the industry or the manufacturing industry does not distinguish anymore within their solutions they require whether this is IoT, IIoT, or whether it's a fourth industrial evolution. The key is that the goal to be able to connect smart products or create smart products within smart factories. And in order to do this, you will need to create a data universe in a hyper-connected world in order to achieve this. And consequently, a data universe was born requiring massive storage capacities realized with the cloud concepts we know today. The challenge remains how to collect the data, how to transform and optimize the data we collect from a suite of applications residing anywhere within a corporate infrastructure. The term smart factory and smart product was created as a result of creating theoretically a data universe in a hyper-connected world. And so again, the challenge is how you connect the individual components, because the components and applications you use, they have a history, they have older generations, and then of course there's a modernization of applications. ERP systems are moving rapidly into the cloud, forcing customers to reintroduce new interfaces, and you constantly have to keep up with the interfacing of individual third-party applications. That's one of the major challenges we face. Consequently, it was actually National Instruments trademarked this term big analog data. And of course, they are offering AD solutions, and they have an interest to use AD cards, for example, to collect this information. However, the key is a source where the data can come from. And the graphic on the left illustrates that data can come from anywhere. And I thought this is a nice graphic to just simply illustrate that it doesn't matter anymore where data come from within a manufacturing environment, outside of the manufacturing environment, because if you look at how you transport your product, you may still want to be able to track the product, but it's all coming back down that you have different means, different methods, different technologies to collect the information from anywhere. And the types of data sources include the entire spectrum available in our digital world today, from industrial control systems, business applications, even wearables, sensors and devices, open and web data, medias, and location tracking, for example. Consequently, in a world of smarter, hyper-connected devices, machines, infrastructure, and environments, the key to make your operations smarter or more efficient lives within its collective sets of data being collected. Uh, that is the key, that data management, when you collect, does not stop by collecting the data and sending them somewhere else. Data collection must include, in order to act efficiently, must include the management, distribution, and transformation of data. In this context, allow me to introduce deviceWISE. deviceWISE is a data management platform to enable the collection, transformation, management, distribution, and analytics of individual data points, regardless of its origination. This is a very critical point, as you can install deviceWISE on numerous hardware platforms. We support numerous operating systems. So in other words, wherever you need to collect data from, we can position our node, our device-wise software, very close to the edge, for example, and then we can act as relays in order to interface with enterprise systems, cloud systems, as demonstrated on the right side. And we cover a huge amount of interfaces. I like to believe that we have the largest driver base, native driver base to connect to all kind of edge devices, versus all the connectivity available to cover pretty much every enterprise system, from SAP all the way to databases like SQL servers, DB2, whether they are non-SQL databases or SQL-based databases, we have the interfaces to create the connectivity required. To install deviceWISE, only a single installation is required on any hardware or OS to enable all the features as summarized in this image above, including assets, cloud platforms like Azure, AWS, Google, IBM Watson, SAP HANA, or non-prem solutions like SAP or other ERP MES systems. deviceWISE is a very comprehensive solution. It is utilized for many different applications in the world of automation, but it has two fundamental features which are ideal for simplifying global data access and global data management while creating the information data scientists or data analysts require. As a consequence, I like to focus on these two built-in features which operate under the hood of deviceWISE and are a standard built-in feature. In other words, they come with deviceWISE as a core functionality available to you and ready to be used regardless of where you install deviceWISE or how you configure deviceWISE. These two features are called, feature one is peer-link. Peer-link allows you to communicate among any deviceWISE node, and I'll get into the detail of this feature in the next few slides. And then the second feature is called a global variable. deviceWISE itself has a variable concept called a local variable, a static variable, and a global variable. And it is the local variable and static variable are used for the internal and local programming memory representation, if you like, versus a global variable is accessible from any project, from any trigger, from any node, regardless where deviceWISE is running in your infrastructure. Let's look at peer-link in a little bit more detail. Peer-link has all the requirements you will need in order to actually connect a hyper-connected world. It's essential that you provide this functionality because you do want to collect information in time, in real time, as much as possible. And then, of course, you want to collect and gather the information and collect across a multi-cross network. And therefore, peer-link needs to support these features. So the one key deployment features it has is remote device access to and from any runtime platform. What this means is that if you have two nodes, you can access to and from those two nodes any trigger or any global variable. Then, of course, a remote trigger logic execution. You can execute remote triggers which you defined on a different node to collect information if you wish. And then you can, of course, remotely connect to global variables running on any runtime platform. Peer-link is designed to feature the following advanced computing models. It supports integrated distributed processing. For example, remote device variables can be directly referenced and locally utilized. It supports cross-platform data and device sharing. As individual nodes can run within numerous hardware platforms and operating systems, peer-link would allow you seamless access to such systems. So you may run a deviceWISE node on Linux and a second deviceWISE node on Windows, but with peer-link, the information available on each node is seamlessly exchangeable. No transformation, no configuration is required to perform this cross-platform data exchange and device sharing. The next position is a distribution of units of work to remote systems and load balancing. They are well-known computing models required when operating in a hyper-connected world. So load balancing is important because imagine you have hundreds of PLCs. You collect information from these PLCs, and then you want to feed that information to a single database. You can imagine that you can easily overpower the database. So deviceWISE itself has a feature or built-in feature that, number one, it has a store and forward feature where you can store the information in case a connection to the database is lost. Let's say you run a maintenance of a database, the database is not available, but what you cannot afford is lose the data, and therefore store and forward kicks in, and which allows you to store this individually, locally. And when we provides a load balancing that we call this a transport when we connect to databases. You can define as many transports as you like and connections to a single database. And then there is a configuration capability within the transport, which allows you to enable load balancing, and deviceWISE will automatically feed this information through the individual transports to the single database based on load balancing requirements. So you can have multiple concurrent connections to any ERP systems in order to provide the load balancing you need to feed the system. And then, of course, last but not least, consequently, a global variable provides a method to create a unified namespace by organizing data from different sources into a coherent model that can be communicated and easily consumed by different kinds of data consumers. So that's the key. If you have, let's say, 100 asset gateways connected to many edge devices, each of those gateways, if you choose, could have a global variable, which then you can be used from a different enterprise system to collect this information directly from deviceWISE. Or you can even have relay functionality from a server perspective, where you run an enterprise gateway which collects this information, then distributes this to the individual targets, whether it's a cloud environment, an ERP environment, or a database. This will demonstrate really quickly how peeling looks like and what you can do from a functionality perspective. Please understand that the configuration of deviceWISE is done by a workbench. We use the same concept as you have, for example, with MySQL or SQL Server, where literally workbenches allow you to connect to different nodes, and then you use that workbench from anywhere to configure and program if you need the device-wise nodes. And in reference to peeling, you have two options to connect the remote device or connect the remote node. And the difference is if you connect the remote device, you actually point to a very specific device defined on a remote node. Let's say you have two PLCs. You would literally connect to one PLC and you would need a second connection, device connection to the second PLC. Or the other option is you can use a node connection, and then you see in your response to remote PLC 1 and 2 connections, which allows you to access write triggers locally while using the remote connection to the PLCs on a different node. These are is a GUI interface sample. The device-specific configuration, you see on the left side, there is a device type, where you select peeling, and then the next step is on the middle, that you select the device connection, and consequently you have to put in the IP address, and the authentication among device-wise nodes is based on username and password, which is part of a security. which would require, if I would introduce and discuss security of deviceWISE, that probably would take another webinar. But you can define the security individually on each or for each node based on your requirements. You can create different profiles, different users with different access, and the access of device-wise features go all the way down that you actually can limit the access of certain users to individual I/O points where you can enable read or write capabilities. So once you enter the IP address, username, and password, and you give it a device name, or you select the device name, device-wise will automatically connect to this device, and then you can instantly read on the local node those remote I/O data, and peerlink is taken care of that the information is being submitted. So that means that peerlink actually does also the translation. It connects to the device on the remote node. If that device is connected to Rockwell PLC, it will, based on your implementation, automatically collect the data from that Rockwell PLC through a remote node to your local node, and then you can use this to create your composite variables or do your trigger logic or calculations. On the other hand, you can define, instead of a device, a node connection. Same concept, you apply IP address, username, and password. In this case, you do not need to know a device name because peerlink will return all the lists of all devices where you can, which you can use to connect to. This is an example which shows you the trigger logic, how that looks. We have a graphical interface, so there is no need to know any scripting language. The functionality is based on individual actions, and using peerlink on the left side, when you program your logic, you see the device variables. Let's say you want to monitor the system monitor of the remote node, and then you have access directly to the system monitor, which may reside on the device-wise node 2, and then vice versa. On the device-wise node 2, you could actually observe the system monitor on node 1 or a PLC device or any additional information which is connected to device-wise itself. Um, the, the, the interesting thing is that this is completely independent from any runtime platform. So in other words, if device-wise node 2 runs on a Linux platform or even AIX or Unix, different types of Unix systems, then it doesn't matter. Peerlink is transparent, device-wise is transparent on application level. You wouldn't even know the difference. This slide shows just as an architecture of a very well-known OT network where you may have multiple servers connected to multiple gateways, and then the individual gateways are connected to the edge devices, whether they are logic controllers, robots, conveyors, CNC machines, and so on. And what we want to do is how can we connect this infrastructure, and that will be shown on a next display. In other words, you would simply install device-wise on the server side if you wish, or you can only choose one server. It doesn't have to be two servers. That depends on the architecture or IT architecture. And then you install device-wise on those gateways. And then you have immediate connectivity from one node to the other node. And they are remotely connected using peerlink, and you can receive the information from anywhere, regardless of the gateway or the server itself. That's one of the key benefits of using peerlink. There is no configuration required to exchange the information collected on the individual nodes. And the same, of course, is that you can use your trigger logic, which allows you to access the individual nodes as discussed previously to get this information transferred and utilized. So from that perspective, let's switch to the global variable device, the second feature. It is important to understand that a global variable is a logical device with no corresponding physical device. What this means is because it is designed as a device, device functionality within Peerlink is exactly what is being utilized to exchange the information. So it's not like a global storage where you define memory or allocate memory onto global storage. That is part of the global variable that you define your variable structures and so on a local node. But it's the feature that the global variable acts as a device so that can be accessed by using the device peeling feature from any node. What a global variable offers, of course, you can define scalar variables of of different data types. You can define array variables. The most important feature, which sometimes I think people are not really taking advantage of, is define structures. So you can define your own data types, which is very important when it comes to composite variables, that create structures of composite variables or representing composite variables so that it can use this to calculate and fill those structures in order to feed to different systems. And then optionally, a global variable has a feature that you can, that it is memory resistant, or you can select whether or not it's persistent information you need, then it will store this information to the disk in case something happens where device-wise a PC needs to be rebooted or power outage or things like this, that it comes back, the global variable comes back, if you wish, at the state at the time when it was restarted. And then you can, once you define a global variable, remote or locally, you have immediate access to those variables using remote local triggers to process information any further. Here's just a quick view. When we create a global variable, we can define scalar variables or single variables of a variety of data types. So in this case, we would define a variable called GV. I always use GV for global variable Chicago. That's a city, of course. You see the reason a little bit later. And then we add a variable called pressure to the global variable we call Chicago. In the next slide, we see that we define a shift array. Let's say you have several shifts, and the data type of the shift array is int2. So we create 5 elements of the shift array with a data type of int2. And call and add this to the device Chicago. And then the most important thing is that we can create structures, which in this case are called efficiency, and add to the variable. And now the structures, as you can see on the right side, you have the option to create variables, and below you have the option to create structures. And in this case, I already created a structure called efficiency. Then here you see the result of the global variable. You have the variable name, in this case GV Chicago. Underneath you have a machine OEE structure where we can display as part of the structure OEE performance, availability, quality. Then we have a single variable called pressure, and then we have a shift array of 5 elements consisting of int2s. So it is, to reiterate, it is very critical to understand that a global variable device is a logical device with no corresponding physical device. And please note that any device definition can remotely be accessed from any device-wise node using peerlink. Hence, consequently, any global variable is upon definition and start instantly accessible from anywhere within the corporate network universe. Of course, this is based on DM zones and IT permissions, But in order to connect nodes among device-wise, all you would need to do is open a single port because it's TCP based, and you could connect those nodes, which so far most IT departments don't have a problem doing this. It's a different story than if you go to the cloud. We know that sometimes IT departments are very resistant to go from OT directly to the cloud. That's why many times we need a gateway or a relay in between edge gateways and cloud connectivity, for example. So how do we create, in a very efficient way, a global variable? As you can imagine, you have hundreds of thousands of variables in complex assembly lines. You go to OT, you start doing your diligence, trying to figure out to determine the data you really need to collect. One approach is you collect all the data and send all the data to AI systems, ERP systems, but then they have the challenge to figure this out. And my experience has been that they are kind of reluctant collect anything and everything. They are not a garbage collector, if I may say, but they are interested in getting the data so that they can immediately start working on analyzing the data, and the data needs to be real, needs to be consistent, and needs to be precise in terms of which process they represent. A perfect example is OEE, where you use different information to calculate your performance, your availability, and your quality. And that even depends on different departments and different plans because they have different uh, accounting systems, for example, different ways how they run production, and they want to see OEE in different perspectives. That's a composite variable which changes basically not only from customer to customer how you calculate and how you derive those values, but it changes also within global companies from business unit to business unit. So you need to have a very easy way to collect this information, put this information into a well-known structure, and then use this structure to provide the results to your systems who analyze this data. And we created a rule which you see here. And if you identify this rule, it's very easy to convert into a spreadsheet. So you can have as many structures 1 to M as you like. Those are the custom structures for the plant or plant specific structures. And then among the structures, let's say structure 1 represents a city, structure N represents a department, and structure M represents an asset. Then among or below each structure, you can define your individual data points, and then you can create your composite variables based on the data points you collect from the individual structures, which allows you very easily, let's say you have 100 machines under structure M, you have structure N, where you can calculate your OEE information for all the 100 machines as an accumulative result for the structure N. And then you can actually deploy this OEE calculation to the city and get very easily the result for a city, considering the departments and machines, if you wish. So the relationship from the CSV file to the spreadsheet is as follows. So you see here, the spreadsheet has, of course, all the columns. On the far left, we see actually the real PLC read address. You can take this from your Kepware export. You can take this from your device-wise export or any device which you use to connect to your PLC, OPC UA servers, DA servers, device-wise nodes connecting to the PLCs. So those are the real PLC address and the real names. And one topic I like to mention, many times the IO names being used are hard to understand from a analytical perspective, because a data analyst or data scientist don't really know what the pressure means for a certain equipment, what the speed means, what does it mean. So it doesn't say much. Or if you say car handling global, ABM large, or so, it doesn't really can relate that value. But what you can do is you can assign the names, which you see in column 7, and define the data point. So by filling out the spreadsheet and organizing the spreadsheet based on your organization, starting at the plant level and then coming down to the business unit, the assembly stations, individual zones, and asset levels, and we could add more levels all the way to the data point. You can define the structure for your plant, and then if you see on the right side here under global variable, when you select this global variable, you actually see exactly where it's coming from, where it's located. In this case, the humidity comes from New York, department BU, the production line BU1, for example, at zone 1, asset 2, and it's called humidity. And this humidity could be a result of the IO, which you see here, excuse me, which you see here on the line of humidity, for example, and so on. So we literally take your structure, your organization, convert it into a spreadsheet, and then assign the variable names based on your needs to create the information for composite variables. Um, and and this can be done in a very easy way. However, of course, the data scientist or whoever collects the information from OT, that is a task which you have to literally interview OT, talk to the OT people, and get the information. First, you need to determine what's available, and then you need probably have a lot of meetings to discuss which data you want to use for your structure to create the namespace you want to look at. To provide the solution, what needs to be done on device-wise level is that here's an example where you have an edge interface. In this case, it's utilizing a Kepware OPC UA server. We have applications where the OPC UA server is handling, again, tens of thousands of variables, and we minimize this to, let's say, 5,000-6,000 variables, which is collected by an asset gateway, and we use an UA client to connect to the OPC UA server. And then we have an enterprise gateway because there's a zone, a DMC zone among asset gateway and enterprise gateway. IT opened up the port for us so we can directly access the information which we have available here on this level from the asset gateway and send it to the enterprise gateway where we run the global variable you saw on the previous slide. So we're updating our local global variable, which we then use to submit through an HTTP client into an InfluxDB and using the IoT Hub interface to Azure. And for this exercise, we only need 4 actions, which is, of course, first we need an enhanced demand read. And the enhanced demand read is actually executing on the enterprise gateway, reading the information from the OPC UA client and Kepware server in this case. And an import function of the enhanced demand read is being called, importing the CSV file and automatically creating and updating the global variable. We also create it by importing the data as a CSV file. So we have a single CSV file which allows you to configure the global variable, which allows you to create the enhanced demand read action by simply importing, and then it fills in all the links between input IOs and output IOs, which in this case is a global variable. And then you can add an HTTP client and import again the same CSV file, which creates, based on the HTTP client, all the information you need to connect to the InfluxDB. And then last but not least, in this case, we have an encode JSON action because the integrator, which does the Azure analysis, told us he would like to know, would like to have a JSON format to make it easy for him to interpret all the values of all data coming up. So we have an encode JSON action which converts the same CSV file into a JSON format, which then you can use using a force action, send telemetry to IoT Hub data, which you can use to send the string or as a string to the IoT Hub, which makes it very easy for the integrator on Azure to process this information. So as you can imagine, you could standardize across any of your plant, and this is certainly the simplest way to integrate and to collect and manage and forward. But let's assume this is now one solution you have for data collection for your AI systems, Azure, or whatever you use to analyze your data. Let's say you do this on a city-based introduction, then you can use this concept, and as a consequence, you create literally a global view of a unified information space without any effort except writing the individual trigger for each plant. So if you have a plant in New York, plant A, plant N, plant M, you can actually have a global view, a global system, which allows you to look at each individual global space for each city, or you can use a different summary of all the cities and create an additional global space. So the most important thing about this is to identify that the conclusion, or basically the conclusion, is that by using the concept of global variables combined with the power of peeling, a standardized global information representation can be created, allowing you to not only use and incorporate existing systems, but scale and expand as you build your systems. And the reason you can build and expand on it, because each global variable you see there, in this case, 4 global variables residing in each city, you can remotely edit, you can remotely change by maybe you want to add another variable to a structure. And so it's manageable through the capability of peeling because you have access to all the space. You can choose to create a single namespace. You can choose to create structured namespaces. The design, the architecture of your namespace is up to you. And of course, security features and store and forward for all upstream data transactions ensure the data integrity actually. So with this, I like to conclude my presentation. And again, thank you so much for this opportunity to introduce a solution and concept to standardize your namespace and access to your data sources. Thank you very much.
Thank you, Gerhard. Real quick, just before we get to the questions, audience, I am going to drop a poll on your screen now.
Okay.
If you would like to have one of our experts contact you directly, and please just respond here on the poll and we will have someone reach out to you. We do have time for a few questions. Still time to ask a question, so feel free to submit using the box at the bottom of your screen. Gerhard, we've gotten just a couple, so let me ask you this first one. It says, so I know I need to collect data, but what data do I need to collect?
That's a very good question. The general or summary answer is that, of course, the data you need to collect must support your objective, and it must be aligned with key metrics which come from reliable sources. This is one of the challenges when collecting data, to make sure that the data you collect have the integrity and the consistency and don't represent any kind of faulty values. Nothing is worse than when you collect data that and it's not consistent, it's not reliable, it may not even represent. And then when you create your composite variable out of many data points, your result will always be wrong or will not be correct, and you cannot use those data. So one of the main challenges is that you have to introduce steps and take considerations to help you identify the data you need to collect. And there are some about 8 steps you should consider, which is, for example, the most important step, of course, is to iterate and refine your data collection, because you probably have to go back many times to do this. You have to define your objectives. You have to understand your stakeholders' needs. So people, the data scientists requesting this data, they need to understand what you are collecting. And then, of course, you have to consider the data sources. Sometimes data are simply not available. If we look at older machines, if we look at CNC machines, sometimes the information we would like to have is just not available because it wasn't integrated at the time when the machine was put in the assembly line, for example. And then, of course, last but not least, you have to ensure the data quality. You need to make sure that the data quality is consistent and is actually real and represents a true value. It doesn't help, and that's sometimes a challenge to perform. Um, and that is actually the part of this integration of creating your namespace and creating the data for your namespace, which takes most of the time. It can take up to weeks or even months based on the size of your project when you want to do the data collection.
Great. And this next question is perfect timing because you just mentioned namespace. What is the importance of defining a namespace?
So there are several important reasons why you want to define a namespace. They are the first and most important namespace is to avoid name conflicts across platforms, across solutions, across locations, plant one versus plant two, and so on. So a unified namespace ensures that every entity, whether they are file-based, variables, functions, or devices, that they have a unique identifier. When we look back at our spreadsheet, that spreadsheet, when you import that, would actually tell you if the name you use does already exist or is a conflict with another structure you're trying to use. Because sometimes you have many layers of data where they come from. That is, and you may not know, but you create conflicts. So the import itself is smart enough to identify, avoiding, or ensure that name conflicts are avoided. Then you want to have an organization and structure for the namespace, because as we have seen, if I may go back, when you look at this global variable on the top right, you see here the total name of the variable humidity, and that is a unique name only existing on this level. Because the zone 1 may have many humidities, but asset 2 has only one humidity, not 2 or 3 or 4, otherwise it would be a conflict. So this global variable not only allows you to see the what this value really, or process value, represents, but it also shows you exactly the location and where it is within your structure of your corporation. That's very important. Then, of course, you have to facilitate communication. In other words, when you create namespaces, that among your networking requirements, among your distributed systems, then the namespace allows different components on nodes to communicate effectively. And we realize this by using peerling. Peeling is the engine underneath the hood of deviceWISE, which manages your namespace locally or remotely due to its feature built into peeling. There is no need that you have to define a protocol, a message, or different tags on different levels. The incorporation of the namespace can be globally managed by deviceWISE. And then, of course, as a consequence, once you do these steps, then it will certainly simplify the maintenance because changes can be implemented more efficiently. Because, for example, administrators or developers can easily understand where and how changes should be applied without impacting unrelated parts of the system. That's all part of the global variable management using the workbench in this case. And last but not least, you have a scalability because, as I mentioned before, a global variable can easily be extended by adding structures, by adding single variables. And then when you store this information, it's not like that the old structure is being destroyed. You just expand upon an existing structure. Or when we go back to the globalization of your global company, you know, the if we use the concept we demonstrate or illustrate here, the New York solution can be identical, can be duplicated to plant N, M, and A if we choose to use the same concept for all the plants. So it's a matter of exporting the deviceWISE project and importing it into plant N, plant M, and you have instantly um, the connectivity to the information. Of course, that assumes that plant N and M uses the same name space convention or the same values. However, if not, it would be easily to replace by simply modifying the CSV file. So there's nothing wrong with having different CSV files, creating a namespace for New York, for plant N, M, and A, for example, and then you import the CSV file, but the logic, the functionality remains the same.
Okay, great. Yeah, that was a really good explanation there. We are getting close to the hour mark, so I am going to take just one more question here today. Why do I need distributed processing when collecting data?
That's an excellent question. Thank you, Amanda. In general, distributed processing is essential for efficient and effective data collection because it enables scalability to handle large volumes of data, because it improves performance through parallel processing and enhances fault tolerance and reliability. These are all features distributed processing brings with it as a consequence of having the ability to connect to those remote systems. So, in other words, it's one thing to have a data collection on a local node, whatever application you're running, and then you have to send a message or send a request through a specific protocol, whatever you use, REST API, HTTP, to a remote node to get this information. Imagine you have thousands of nodes and you start creating a layer of messaging among all the nodes. That's a nightmare um, of configuration. That's a nightmare of um, uh, realizing the integrity of the data because communication is you would need to put in fault failure modes, repeat messages, repeat protocols, and so on. And so it would be very challenging to provide the scalability. While if you have a distributed processing, and by using peelings, those features for integrity are all built in. You don't have to worry about if something is not connected or connection fails, depends on the level we can store and forward. But it's much easier to ask the remote device which is directly connected to the edge, providing the information I need, than having to send a message through a third-party solution or product, and then I have to maintain that level. And in addition, because of this, it of course improves the performance through parallel processing, because I can send out the information to all 4 planes at the same time, and I get an instant response. Whereas if I would use layers of third-party applications, then if I think about MQTT, for example, you have to go through Progress, and then there's no guarantee that you get any response, or the data may be delayed. So it's a challenge. So that's why the network layer for you to manage globally distributed namespaces needs to have the ability for distributed processing.
Great, thank you so much. I believe that is all the time that we have for today. I realize that we didn't get to a few of these additional questions, so we'll be sure to have somebody reach out to you directly to answer those. Again, please be sure to check your inboxes in the coming days for that replay link, additional resources here in the resources section. And Gerhard, thank you so much for your time today. I really appreciate it.
Thank you, Amanda.